So I want to start off looking at just a couple of things from the out of class exercises from S5. Just to make sure everybody is on the same page with stuff. So I'm going to look at problems 1 through 3, basically. We're given that average temperature data from 1991 to 2000. And the numbers we have there, 77.7, 74.2, 80.2, 79.4, 79.2, 73.4, 75.8, 76.5, 81.4, and 72.3. And we are asked to find the standard deviation for that. And it does tell us this is a sample, so we're using a sample standard deviation. So remember, for standard deviation, it is a 6-step process. Can anybody tell me what step 1 is? Yeah, step 1 is find the mean. So the mean is just, we're going to add up all of those numbers and divide by what? Well, how many numbers are there? There's 10, so we would divide by 10. So let's go ahead and we'll add those up. I'm just going to pull my calculator over here. 77.7 plus 74.2 plus 80.2 plus 79.4 plus 79.2 plus 73.4 plus 75.8 plus 76.5 plus 81.4 plus, I'm going to cheat, 72.3. This is the last one. Now remember, I warned you yesterday, when you add these up before you divide, make sure you hit equals first, and then we can divide by the 10. So we get 77.01 is the mean of these numbers. So anybody have any questions on how to calculate the mean? Okay, that's just basically the average that we've always done. Okay, so then step 2 is to do what? Yes, subtract the mean from each number. So we're going to subtract 77.1 from each number, or 77.01. So 77.7 minus 77.01 is 0.69. 74.2 minus 77.01 is a negative 2.81. 80.2 minus 77.01 is that 3.21? 79.4 minus 77.01 is 2.39. This should be 3.19, shouldn't it? 3.19, 2.39. 79.2 minus 77.01 is 2.19. 73.4 minus 77.01. Oh, what is that? Negative 3.61? 75.8 minus 77.01 is negative 1.21, I believe. 76.5 minus 77.01 is a negative 0.51. 81.4 minus 77.01 is a 4.39. 72.3 minus 77.01 is a negative 4.71. Now, if we were to add all of these up right now, this should add up to what number? We should get 0 there. So let's double check that. So 0.69 plus negative 2.81 plus 3.19 plus 2.39. Again, this isn't part of the calculation. It's just double checking to make sure we're not way off. Plus negative 3.61 plus negative 1.21 plus negative 0.51 plus 4.39 plus negative 4.71. We get a negative 0.83, indicates we're off a little bit. Did I forget anything as I was entering them there? Yeah, it looks like I did miss a number as I was entering there. Usually the only reason this would be not 0 would be if there was something wrong with our mean. Okay, so we might be just a little bit off, but let's keep going with it and see. So then what is our third step? So we're going to square each of these. Remember, those numbers are called the deviations. We're going to square the deviations. So I have 0.69 squared is going to be 0.4761. Now you have to be careful on your calculator to the negative 2.81 when you square that. You have to put it in parentheses like this. Otherwise, if you just type in negative 2.81 and hit squared, it's going to try to tell you that it's negative, and it's not. Anything squared better be positive. This is 7.8961. The one left off the end there. Then we're going to do 3.19 squared, 10.1761, 2.39 squared, 5.7121, 2.19 squared. As you can see, this is a very long process, even for just 10 numbers. 4.7961. The negative 3.61 squared, now remember that's negative, so again we got to put it in parentheses. 13.0321. Negative 1.21 squared. I'm just going to put in 1.21 squared because we know it's got to be positive. 1.4641. The negative 0.51 squared. 0.2601. And 4.39 squared. 19.2721. and the negative 4.71 squared. Giving us 22.1841. So that is our squared deviations. What's step 4? Find the sum of those, add those up. Very good. So let's do that quick. Okay, get them all punched in. We get 82.269, looks to be our total. Now then, step 5 is the part that was a little bit tricky. Step 5, I heard you say it, Sam, it's to do what? Divide by n minus 1. So there are 10 items in the list. 10 minus 1 is 9, so we're going to divide by 9. So dividing by 9 gives us 9.141. Yeah, because there's 10 numbers in the list. So one less than that would be 9. Now most of the sets we've done have had 10 numbers in the list. So that's why we've almost always divided by 9. This number right here, after we divide by n minus 1 there, is what's called the variance. To find the standard deviation, there's one more step. That is perfect. The square root of that result is step 5. So the square root of 9.141. 3.02, we're going to call it. So that's our standard deviation. So now the question is, what does that standard deviation mean? If we were asked to interpret the standard deviation, like we're given in step 2 there, what does that mean? What that means is, on average, data points, in this case, the mean temperatures are 3.02 degrees in this case from the mean. Remember, we found that mean in step 1, which was 77.01 for that set of data. So over those 10 years, the mean was 77.01. On average, each temperature is 3.02 degrees away from that mean. Any questions on that? So if we were asked then which temperature is most unusual, we could actually go back here and look at the deviations and see which one is either the largest positive or negative, and that would be this one here. So that 72.3 is the one that is the furthest away from the mean. Okay, so today we want to talk about interpreting this standard deviation a little bit. What does the standard deviation tell us? So we're looking at S6 here, and in S6, problem situation 1. Sure. Which one? Okay, so number 5, the dot plots display the monthly precipitation from April from 1981 to 2015 for Cleveland, Ohio, and Portland, Oregon. Okay. So those dot plots that they have set up there, you can see for Portland, it looks to be like there's a lot more dots on the left side of the plot. Which city has the greater variability in April? For that, I would just look at how wide they're spread out. It looks like Cleveland is more spread out for A. And I know you're asking about C, but I'm just kind of working my way up to it here. Estimate the range for each. Well, that would just take the highest one for Cleveland is just under 7. Looks like 6.9. The lowest one looks like 1.4. So 6.9 minus 1.4 would give you 5.5 for Cleveland. And Portland, it looks like about a 5.3 minus exactly 1. So that's a 4.3 for Portland. So then finally C, which I know is what you're asking about. Mean April month precipitation for Cleveland and Portland is 3.6 inches and 2.8 inches respectively. Would it be reasonable to estimate the standard deviation of Cleveland's April monthly precipitation is 3 inches? And Portland, okay, so let's look at this. The mean for Cleveland is 3.6, which looks about right. And for Portland, 2.8, which is about in the middle of that 5.3 and the 1. The standard deviations say, would it be reasonable to estimate the standard deviations for Cleveland is 3 and Portland is 1.5. Okay, so what we're going to do is we're going to look at it this way. Here's Cleveland. The smallest number for Cleveland of course, helps if I draw my number line big enough. Let's try that again. So we're going to go 1. Okay, so for Cleveland, we're going to put these dots on the top of this number line. Our smallest is 1.4 right here. Our largest is 6.9. The mean is 3.6, so right in here. If I estimated the standard deviation at 3, that means one standard deviation would go down to about 1.6. And going up would go up to about 6.6. That's, oops, no, it wouldn't be 1.6 down here, it'd be 0.6 down here, wouldn't it? Like that. So one standard deviation would really contain the whole set of data. What that's saying is, if the standard deviation was 3, I mean, there aren't any points that are more than 3 units away on the bottom end down here. That, to me, that's too big of a standard deviation for this set of data. A rule of thumb, by the way, for a small set of data is you should have at least 2 standard deviations between the mean and the smallest number, and at least 2 standard deviations between the mean and the largest number. So that's way too big for Cleveland. Let's look at Portland. Portland's smallest number was 1. Largest number was 5.3. Their mean was 2.8, so that's right in here. 1.5 would take it down to 1.3 and up to 4.3. That's a lot better. That might be acceptable, the 1.5. I would still say that looks like it might be a little large, but it might be acceptable. But the 3 for Cleveland is definitely too big. The 1.5 I'd maybe say is a maybe. You bet. In fact, what we're going to do today will explain that a whole lot better. So there's 2 topics I want to cover today. The first topic, we're going to be talking about comparing items from 2 different populations. So we are looking on S6 here, that problem situation 1, and temperatures are rising is the title. So what they're looking at here is they're taking climate data in several different regions. And do you guys not have S6? Okay. Well, here, I'll pull it up so that we've got the material in front of us then as we look at it here. Yeah, I can do that for you. Need all of them done for S? Okay. Okay, so let me get down to unit S here. Here's actually what we're looking at right now. So what we're talking about is they're looking at the temperatures rising. What they've done is they found a 30-year average monthly temperature for different regions. And the reason they go over 30 years is, of course, it's really easy to have a couple of years in a row. Like, 4 or 5 years ago, we had 2 winters in a row that were just horrible. We had a winter where there was a lot of snow, and we actually had measurable snow on the ground 9 months in a row. From the end of September until the beginning of May, we had measurable snow on the ground. The following winter was one of the coldest winters in history. So it's not uncommon to have 1 or 2 years where we have extreme temperatures. So that's why they use that 30-year average to make comparisons. So what they've done is they've given us here 30-year averages for 6 different major stations. And they've given us the mean and the standard deviation for each of those stations. Now, central Massachusetts, and each of these actually is a composite of temperatures taking from, more than one weather station within that region, and then they put those together to come up with that mean temperature. So we've talked a little bit already about some reasons why they might take a 30-year temperature norm. Why does taking that 30-year temperature norm make the data more useful? Now, we talked about the data be going up and down. What are some other reasons why using 30 years might be useful? Okay, yeah, we talked about it a little bit on Monday. We talked about those cycles in the climate. If we just take a window here, it looks like the temperatures are falling. If we took a window here, it looks like the temperatures are rising. 30 years should be big enough to get a complete cycle in. So we're not taking a window of just, a small window. So that's very good there. The other thing 30 years does for us, in statistics, 30 is kind of like a magic number as far as sample size. If you get samples that are bigger than 30, things tend to just be a whole lot neater. So the standard deviation works out better. The more samples you take, the more accurate that standard deviation is. If you have just a few samples, just a few years, that standard deviation ends up being huge because the numbers can jump around a little bit. The more numbers you have, the smaller that standard deviation becomes. So the Central Massachusetts Climate Division is approximately 42,000 or 4,200 square miles. Their data is collected from several different stations in this region. Now note that the stations are not evenly distributed. So if this is the area where that is collected from, there might be a station here. The next one might be here, but there might be one close to that. They might be spread out. They're not necessarily evenly spread out. So how would you go about combining temperatures from those different regions so that you get an actual composite for the whole area? Any ideas? Well, one idea might be just to find the mean or the median. But that would not take into account the fact that Station A here is covering a whole lot of area where Station C is kind of sandwiched in between ones here. So how could we account for, using stuff we've already learned, how could we account for the fact that Station A covers so much more area than Station C? In fact, Station F covers a lot of area compared to like D or C. Do you remember anything we did right at the beginning of Unit S? How did we calculate GPA? But remember, we also had to account for the number of credits per class, right? So we called that a weighted average. So what we might do is we might take that temperature times the area that weather station covers and do that for each weather station, and then in the end, divide by the total area. And what that does is the weather station that covers the most area, that temperature gets weighted the heaviest because that temperature occurs in the most places. Okay, July average temperatures have a mean of 70.7 degrees, standard deviation of 1.6. Both of these statistics are based on 30 July average temperatures from 71 to 2000. So this is what we were talking about from the out of class exercises from S5. What does that standard deviation of 1.6 degrees Fahrenheit mean? Okay. About how close? Remember, what the standard deviation is telling us is on average, temperatures are about 1.6 degrees Fahrenheit away from the mean of 70.7 degrees Fahrenheit. So what that's saying is on average, those temperatures are about 1.6 degrees away from it, higher or lower. So now we want to compare South Central Florida's July temperature to Southwest North Dakota's July temperature. Well, if we compare that, South Central Florida had a mean of 81.8 and a standard deviation of 0.8. Southwest North Dakota had a mean of 69.0 and a standard deviation of 3.1. So what is the mean, first of all? If we can compare means, what does that tell us about the two regions? What can it tell you about the temperature of the two regions? Yeah. So the fact that South Central Florida has an average of 81.8 and North Dakota, Southwest North Dakota has an average of 69.0, what would that tell you about the climate in those regions? You're thinking too hard on this one. Which one's warmer? Florida, definitely. And that's what the temperature, that's what that mean is telling us, is on average, Florida is a lot warmer. In fact, it's like 12 to 13 degrees warmer. So then the next thing is, what do these standard deviations tell us? Well, if I'm looking at that, which one has, which area is more likely to fluctuate away from that average temperature more? North Dakota, and what makes you say that? Yes, it's a bigger standard deviation. So that means if we were tracking that temperature from day to day, probably a lot more up and down for North Dakota. For South Central Florida, 0.8 is a really small standard deviation, probably not huge fluctuations from day to day for South Central Florida. Where Southwest North Dakota, 3.1 degrees, that's a lot of fluctuation in temperature. Okay, so now let's try to compare things a little bit more precisely. So a temperature anomaly is a temperature that is very different from what would be the normal temperature. Like this summer, we had evening temperatures in late July that dipped down into the low 50s. That's an anomaly. That's not normal. In fact, the second weekend of September, I was camping and it hit 43 degrees outside while I was camping at night. Yeah, that was not pleasant. So those are temperature anomalies. Well, how do we compare, since these regions are so different? You know, Florida here is the mean of 81.8, and South Dakota or North Dakota has a mean of 69. How would we compare temperature anomalies from one place to another? And that's where this idea of a Z-score comes into play. The Z-score is equal to the value that we're looking at minus the mean for its population divided by the standard deviation. So let's say that we're looking at Central Ohio. If you looked up on your chart for Central Ohio, the mean temperature is 73.3 degrees and the standard deviation is 1.8. Do you guys have your print off yet so I can switch back to the regular screen? Not yet? Okay, so we'll keep this up here. I'm going to blow this up a little bit to make it a little easier to see. There. I'll make that a little easier to see by making it bigger like that. So anyway, what they want to do is they want to compare. Now, this is Remember, this mean and standard deviation, that came from 1971 to 2000. So they're looking at July 2013, 2014, 15, and 16, and they want to see how those temperatures compare to those 30-year averages from 71 to 2000. And to do that, they're going to use this Z-score thing. So for July 2013, they found an average temperature of 72.8. To find the Z-score, it's a two-step process. We find the difference, that's just this right here, the value minus the mean. But 72.8 minus the mean is 73.3. So that difference is negative 0.5, right? So being negative 0.5, let's see if I can erase that, make it a little clearer. There, negative 0.5. So that's saying that's 0.5 degrees away from the mean. But in order to make this so that we can compare it to other areas, we got to finish the Z-score, and that next step is to divide that difference by the standard deviation, which is the 1.8. So negative 0.5 divided by 1.8 ends up giving us negative 0.3. That's our Z-score. So now what does that Z-score mean? Well, that means that this temperature, 72.8, the negative says it's below the mean, 0.3 says it's 0.3 standard deviations below the mean. So that's saying it's relatively close to the mean. Now let's look at 2014. I'll walk you through this one, and then I'll have you do the Z-scores for the next ones. So 2014, that temperature is 69. So the difference is going to be 69.5 minus that mean is 73.3, which is going to be what? 3.8? Negative 3.8 degrees is the difference. The Z-score, negative 3.8 divided by 1.8. Now, typically, we're rounding our Z-scores to one decimal place. So negative 3.8 divided by 1.8 is a negative 2.1. So what that is telling me, the negative is telling me that that temperature is still below average, and it's 2.1 standard deviations below the average. So I'm going to give you guys a couple minutes. I want you to find the Z-scores for 2015 and 2016 there. Okay, so for 2015, our difference, 71.7 minus 73.3, that's a negative 1.6. So then our Z-score would be that negative 1.6 divided by the standard deviation of 1.8, which is going to be a negative, it's actually negative 0.888, but we'll round it to negative 0.9. So again, that's below the mean, and it's about 0.9 standard deviations, not quite one standard deviation below the mean. Next, we have the 75.2 in 2016. So 75.2 minus the mean is 73.3 is a positive 1.9 degrees. So we take the positive 1.9 divided by 1.8, ends up being a positive 1.1 for the Z-score. So a Z-score of a positive 1.1, positive tells us it's above the mean, and it's a little over one standard deviation above the mean, 1.1 standard deviations above the mean. So looking at 3 out of those 4 years, yeah, it's like 1.05, but I rounded it up to the one decimal place. No problem. So again, 3 out of those 4 years, the temperature was below average. Now what we want to do is we want to look at then some temperatures during those times for southwestern North Dakota and for south central Florida. Did you get the paper, Sam? Okay. Jocelyn, you have it in front of you? Yes? Okay. So I can put this aside here now for a while. So what I want you guys to do, it's actually time to take a break. We're going to take a little bit of a break. Let's come back at 11:30. And when we come back in, I'm going to have you guys find the Z-scores for those temperatures in North Dakota and for the temperatures in south central Florida. So let's go ahead and, like I said, take 10 minutes and we'll, at 11:30, we'll look at these. So I'm going to have you do now for North Dakota. North Dakota, the mean is 69.0 and the standard deviation is 3.1. So I want you to find the Z-scores for these 4 temperatures. 68.6, 67.1, 69.9, and 70.2. So I'm going to give you a few minutes to find those Z-scores. Remember, you find the difference and then you divide that difference by the standard deviation. So I'll give you about 2 minutes and then we'll look at those Z-scores. So what'd you guys get for a Z-score for the 2013 temperature of 68.6? Negative 0.13. Okay, we're going to round it to negative 0.1. How about then for the 2014 temperature of 67.1? It's negative 0.61, so we'll round it to a negative 0.6. Yeah, we're going to 1 decimal place. It looks like they want it rounded to. Then for 2015, a temperature of 69.9. 0.3, good. Now that one's positive because it's larger than the mean. And then finally, for 2016, the 70.2 is 0.4. Now remember what those are telling us. The negative ones are smaller than the mean. Negative 0.1 means it's 1/10 of a standard deviation below the mean. So it's just barely below the mean. Yeah, basically, Sam, all it is you're going to take this number here, 68.8, subtract the mean of 69.0, hit equals, and you're going to take that result divided by the standard deviation of 3.1. So it's a negative 0.1. Yep. So a negative means it's smaller than the mean, and the 0.1 means it's 1/10 or 0.1 standard deviations below the mean. Then for the 67.1, we do the same thing. 67.1, we'll subtract that mean of 69.0, which will give us a negative 1.9. Then we divide that negative 1.9 by the standard deviation of 3.1. That gave us the negative 0.6. So what this is telling us, 2 of those temperatures, these 2 were smaller than our mean temperature, were colder. These 2 temperatures were warmer than our mean temperature. Let's look at Florida now. So Florida has a mean temperature of 81.8 and a standard deviation of 0.8 degrees. So let's look at temperatures for Florida. 81.3, 82.2, 82.3, and 84.2. So find the z-score for each of those temperatures for Florida's mean and standard deviation. I'll give you about 2 minutes to work on those.
0.8, but I accidentally typed in 8 before the 0. Do I have to restart the entire thing, or can I just do?
Just move your decimal point. What'd you get?
Well, no, I'm asking like, oh, well, I was asking like in my calculator, do I have to type in the whole thing again, or can I just do 0.5?
Oh, you could just do 0.5 divided by 0.8. Gives you 0.6. Well, it's 0.625, but we'll round it to 0.6. The 82.3? July? Yep. Perfect. Struggling to get the keystrokes in the right order? Struggling to get the keystrokes to stay in the right order for you? Sure. Okay. So let's take a look at the 2013, the 81.3. What did we get there? Negative 0.6. Good. How about for 2014? 0.5. Good. And we've already did the 2015, comes out to 0.6. 2016 is 3.0. Yes. Because you did that, you subtracted 81.8. You got a difference of positive 2.4. You divide that by 0.8, it's 3 above. Now, if we look at that 2.4 difference in temperature, if we go back up to North Dakota up here, there were some up there that had some pretty big differences in temperature, but they had fairly small z-scores. Why is it that those big differences in temperatures gave small z-scores for North Dakota, but large z-scores down here for Florida? Exactly. Because North Dakota has a large standard deviation, a 3.1, it's more common for their temperatures to vary a lot more. So because of that, the z-scores are smaller. So being 2 degrees away from the mean in North Dakota isn't a big deal. That's only a z-score of negative 0.6 or positive 0.6. Being 2 degrees away from the mean in Florida, well, with a small standard deviation, that's a bigger deal. That's going to be a 2.5 z-score. So what this z-score allows us to do is we're comparing each data point to its own population so that it's called standardizing it. So here, what we're looking at here is, let's look at this temperature here for 2013 in Florida, and we're going to compare it to 2014 in North Dakota. The difference in North Dakota was negative 1.9 degrees. That gave us a z-score of negative 0.06. Well, in Florida here in 2013, we also had a z-score of negative 0.06, but that was just a negative 0.5 degrees away from the mean. So because the standard deviation is so much smaller, being a half a degree below mean is just as big of a deal in Florida as being 1.9 degrees away from the mean in North Dakota. So which of these places had more extreme differences in temperature during those years? Florida, North Dakota, or we also did Central Ohio. Well, which one had the largest Z-scores? Here, let's put them side by side. We have Ohio, North Dakota, and Florida. For 2013, Ohio was a negative 0.3, North Dakota was a negative 0.1, Florida was a negative 0.6. Well, first of all, what can we say about all three of those? Since they're all negative, what does that tell us? What's the negative Z-score say? The negative Z-score means that the temperature or whatever the value is below the mean, less than the mean. So what that's saying to us is that all of those temperatures are below the mean temperature for those areas. A negative Z-score. Negative means less than the mean or average. Positive means greater, than the average. Above average, very good. So all three of those were negative, so that means that for all three of those areas, the temperature was below average for that year, on that year. Now, 2014, Ohio was a negative 2.1, North Dakota was negative 0.6, Florida was a positive 0.5. Now, what can you say about those temperatures, those Z-scores? First of all, are they all below or above the mean? But careful. Two of them are negative, right? So these two, Ohio and North Dakota, had temperatures below the mean. What about Florida? Florida's above because it's positive. Which temperature, which region had temperatures that were more extreme? So here we're not looking at the positive or negative, we're just looking at how far it is away from zero. Which Z-score here is the largest positive or most negative? Yes. So again, which one is the most extreme temperature out of these three? Well, if we go through them, this one is saying it's negative, so it's less than the mean. 2.1 means it's 2.1 standard deviations away from the mean. This one's negative, so again, it's saying it's less than the mean, but it's 0.6, so it's only 0.6 or 0.6 standard deviations from the mean. This one's positive, so that means it's above the mean, but it's only a 0.5, so it's only 0.5 or half a standard deviation above the mean. So which one of these regions has a temperature that's further away from the mean?
2.1.
Yeah, the 2.1. That is more standard deviations from the mean. So for that year, we would say Ohio had the most extreme temperature. Now, if I go back to 2013, would I say any of these are really extreme? Not really. No. 0.6 is only 0.6 of standard deviation. That's not a big deal. In a little bit, we'll look at a bell curve, an empirical rule. It'll give us some percents that kind of go along with those. Now let's look at 2015. Ohio was negative 0.9, again, telling us it's below the mean. North Dakota was 0.3, so that's positive, it's above the mean. And Florida is 0.6. So summarizing this, we can say again, Ohio was below the mean, while both North Dakota and Florida were above average temperatures that year. But would you say that any of them are extreme? No, they're all within one standard deviation from the mean. So then finally, let's look at 2016. Ohio was 1.1 Z-score, so that's above the mean. North Dakota was 0.4, that's above the mean, it's positive. Florida is also positive at 3.0. So all of them are positive, which tells us all of them were greater than the mean temperature. Would any of them be considered extreme? Yeah, the Florida 3.0, that's 3 standard deviations away from the mean. I would say that might be an anomaly. That might be an anomaly. The 1.1 for Ohio, that might be on the borderline, but I'd say probably not yet. So the two temperatures here that I would say were probably anomalies are the Florida temperature in 2016 and the Ohio temperature in 2014. The rest of those I would say are probably right in the ballpark. Now I'm going to skip over a couple of things here. I'm going to skip over number 8, the dot plot, and I'm going to go to number 9. Number 9 is taking temperature anomalies from 20 different climate divisions over a 4-year period. So that means there's 80 anomalies being graphed here. And what they've done is they've made that bar graph, it's actually called a histogram. I'll actually scroll down to it here. Right here, this histogram to plot those anomalies. So what they're saying is they've grouped the Z-scores. So right here, this bar is Z-scores that are between 0 and positive 0.5. And that's telling us there were 11 of those 80 temperature anomalies, 11 of them had Z-scores between 0 and 0.5. So I wouldn't consider those to be very unusual. Up here, these are ones that had Z-scores from 3 to 3.5. Trace that over, there's one of those. So only one of those temperature anomalies were 3 to 3.5 Z-scores above the mean. It looks like there were 2 that were between 3.5 and 4 standard deviations above the mean. What I really want to point out on this graph is what would we expect the Z-score of the mean to be? Well, let's take a peek here. If we have a population with a mean, and I'm just going to use simple, easy numbers for us, a mean of 20 and standard deviation of, oh, let's just say 5. What is the Z-score of 20? What do I do with that? I take 20 and I subtract, what do I subtract from this 20? Remember, it's the value, and then I subtract the mean. So I subtract the mean, which is 20, gives me a difference of 0. Then I divide that 0 by the standard deviation of 5, which gives me 0. Good. The z-score of the mean is always going to equal 0. So if I have a temperature that's right at average, that temperature should have a z-score of 0. So now I'm going to go back to this plot of z-scores. I would expect that most of these z-scores would be close to the mean. The mean would have a z-score of 0 right here. So I would expect this plot to kind of peak at the mean. But is the peak of this plot at the mean? The peak of it's right here, isn't it? Is that peak at 0? No, it's not. This is 0.5 to 1 here. So what that is telling me is that these temperature anomalies, a z-score of 0 here would mean that that temperature anomaly was exactly at the mean. So, but this is telling me there's way more positive z-scores than there are negative z-scores, which tells me that there's a lot more temperature anomalies that are above average than there are ones that are below average. This is one of the things they use as possible evidence that temperatures might be increasing. Okay, so I want to talk a little bit about, I'm jumping ahead a little bit. This is not something that'll be in the homework, but it's something I really wanted to talk about with you. I can get down to it here. Here we go. That's not quite it yet. So anyway, we've talked about these curves and we've talked about z-scores. Remember the data distribution is this bell curve here that we're talking about. The center of that bell curve is the mean, median, or mode. We're just going to talk about mean or median for right now. We're going to use the mean as the center of that bell curve. As you go out with z-scores of 1, 2, or 3 on each side, so in positive 1, 2, or 3, or negative 1, 2, or 3, the power of that standard deviation becomes evident because the data tends to be distributed in a certain way according to that standard deviation. For example, between the mean and a z-score of -1, if it's a normally distributed set of data, 34% of the data, 34% of the items in that set will have a z-score between 0 and 1. In other words, 34% of the items in that set will be between the mean and 1 standard deviation below the mean. Now the same is true above the mean. 34% of the items in that set will be between the mean and 1 standard deviation above the mean. Now if we keep going out, to a z-score of -2. Well, between a z-score of -1 and -2, 13.5% of the data will fall between a z-score of -1 and -2. And again, this is symmetrical, so the same is true on the other side, between a z-score of +1 and +2. And these percents are always the same, no matter what set of data we're looking at. So what would we possibly use this for? Well, there's actually a lot of things we can use it for. So I'm going to set up my curve here. Remember, the center here is the mean, and I go out 3 standard deviations on each side. This is 34%, 13.5% between 1 and 2 on each side, 2.35%, and then 0.15% on the very tails. Remember, we said this is a z-score of -1, -2, -3. This is a z-score of +1, +2, and +3. Well, what does that mean? Well, let's say you are looking to buy a house, and you want to buy a 3-bedroom, 2-bathroom house. And you do your research, and you look in the area that you are looking to buy, and you look at the houses sold in the last several years, and you find that the houses sold that are 3-bedroom and 2-bathroom in that region over the last several years have a mean selling price of $140,000 and a standard deviation of $25,000. So what that means, the mean is 140,000. That's going to be the number that goes in the center here. So that's $140,000 there. This one here, the z-score of -1, that's 1 standard deviation below the mean. Well, that's just going to be the mean minus a standard deviation. 140,000 minus 25,000 is $115,000. And I keep going. The second, the z-score of -2, that would be another standard deviation lower. So I'm going to subtract another 25,000. So 115 minus 25 is 90,000. The z-score of -3 is another standard deviation below. So I subtract another 25,000. So that's going to be 65,000 here. So first of all, are there any questions as to where these numbers here came from? The 65, 90, and 115. Remember, they put the mean in the middle, the 140,000, and then at each step, I just subtracted the standard deviation. I'm going to do the same thing going to the right. +1 z-score means I add a standard deviation. So 140 plus 25 is $165,000. Adding another standard deviation, 165 plus 25 is 190,000. Adding another 25,000 puts us at $215,000. Now remember, we said these percents up here are always the same. Those will never change. So let's take a look at an example here of how you would use this. So let's say you find a house and you just absolutely love this house. It has a selling price of $190,000. Your realtor tells you, oh, that's a great price. You better put in an offer on this home right now or it's going to be gone. Of course, they always say that, right? If you don't put in an offer, and you better offer them their asking price or somebody's else is going to buy it. Well, what does this data tell us? Well, that $190,000, that's this number right here. So if I wanted to know what percentage of houses are cheaper than $190,000, well, cheaper is going off to the left side here. Those are the prices that are cheaper. So here's $190,000. If I add up those percents there, to the left of that, those percents add up to 97.5%. What that is telling me is 97.5% of all 3-bedroom, 2-bathroom houses that sold in this area sold for less than $190,000. So that's telling me that there's probably a pretty good chance that I'm going to find a house for less than $190,000 that I still like. I say something's going funny over here again. So again, like I said, 97.5% of all houses, 3-bedroom, 2-bathroom houses that sold in that area over the last several years sold for less than $190,000. So that tells me I've got a pretty good chance of finding a house that's cheaper that I still like. So like I said, these percents in here under the curve always stay the same. It's these numbers down here that change depending on what the mean and the standard deviation for those numbers are. Like you might be looking at a job offer, and your job offer might be for $18.30 an hour. And you might be trying to decide if that's good pay. Well, maybe where you're living now, that's a good wage, but where you're moving has a slightly more expensive cost of living. So you want to compare to wages in that area. So starting wages in that area. Let's say you do your research and you find that wages in that area, starting wages have a mean, again, this would be starting wage, not just regular wage, has a mean of $16.90 per hour and a standard deviation of $1.40 per hour. So we're looking at this curve again. Now remember, these percents never change. So these percents are constant. What changes are the numbers down here on bottom. What's going to go right here in the middle? That's going to be the mean of 16.9, 1690. If I go one step to the left, how do I get to that number? Perfect. I subtract that standard deviation of $1.40, which gives me $15.50. To get to the next step, I subtract it again, which is $14.10. Get to the next step, I subtract it again, which is $12.70. Going to the right, how do I get this first number to the right? Perfect. I add that standard deviation to the mean. So 1690 plus 140 is 1830. That's really the number we're looking for, so we could stop there, but I'm going to keep going just to fill this in. Add it again, add another $1.40 is 1970, add another $1.40 is 2110. So your offer of 1830 is right there. What that's saying, and I can go one of two directions. I could add up these percents here and say that 84% make less money than that. Or I could add up these percents over here and say only 16% make more money than that. So you know where you land in that curve. So hopefully between the Z-scores and this bell curve here that we put up there, this is called the empirical rule, by the way. hopefully between, like I said, the Z-scores and the empirical rule, this gives you a little bit better picture of how the mean and the standard deviation can be used to look at data and what the importance of them are. That standard deviation is an incredibly powerful tool once you start to understand what it means. Okay, so remember that due tomorrow, and I will go up and open all the Unit S assignments for everybody. But due tomorrow is the out-of-class exercises for S5 and the PNL for S. Actually, I don't think the PNL for S6 wasn't out there, was it? So it'll just be the OCE for S5. Due for Monday, actually, it won't necessarily be due until Tuesday, but for Monday, the OCE for S6. Is it? Okay. So the PNL for S6 is also technically due tomorrow. Okay. So then Monday, we'll do a review. Sam, I'll make sure I have that test up for you so you can take it after class Monday. Otherwise, anybody else, if you want to take it early, you can. Otherwise, on Wednesday, we do plan to just have the whole 2 hours on Wednesday to take the test. The only disadvantage for taking it outside of class is you won't be able to ask me questions, of course. This score will be curved like the others, though. You can try to send me emails during the day. I'll be in class, but I'll have my email open, so I might be able to answer emails quick. If I don't know if they allow you to have access to a computer while you're taking the test or not. Okay. Oh, sure. Okay. Sure. Okay, I'll make sure I specifically tell them that you can use the computer. You can have access to the computer and stuff. Okay, we will see you guys on Monday.